So that's pages 26 and 27 in the printed notes. So what we saw yesterday was how to use R to perform analysis of variance, and in particular how to use that to compare nested models. So you have two models, one of which is nested within the other in the sense it's a special case of the other model with some of the parameters, the coefficients beta, set equal to 0. Some of those coefficients set equal to 0. Okay. So the tables that we get from analysis of variance give us these hypothesis tests where we can use to see whether there is evidence that we should reject the simpler model in favour of the more complicated model. The null hypothesis being that the simpler model is satisfactory. Okay. However, if you look at the way that we did that, you'll see that the variables appear in sequence. Okay, in the way, and the sequence they appear in is the order in which they're put into R. Okay, so when you add a new variable into the model, the sum of squares, the row that appears in the analysis of variance table, depends on what's been put in it before. You're comparing the extra effect of adding that variable compared with the model that you've already got without it, but with the previous variables. So in the analysis of variance table, you add the regressive variables in the order that they appear in the R command. Okay? So that means that the order that the regressive variables have might affect what we conclude, what we decide is the best model using the analysis of variance method. Okay. Occasionally you have a situation where in fact it doesn't matter because the variables, the regressive variables, are completely uncorrelated. Okay. But this really doesn't happen very often. So one situation where it does happen is if you have a designed experiment where the experiment has been carefully designed so that the regressive variables really are uncorrelated. But this often isn't the case. In many settings we just cannot control the regressive variables well enough for that to be the case. So you can't assume that they're uncorrelated. So the order of the terms is actually potentially going to matter. Okay, so let's consider our tractor data set again. So the question that we were looking at yesterday was, is it helpful to add a quadratic term to the model? So we've got this quadratic model, so where we fit the quadratic beta 0 plus beta 1 xi plus beta 2 xi squared plus the random part of the model epsilon I. So that's our quadratic model, and the question is, do we actually need the quadratic term? Can we actually get away with taking beta 2 being equal to 0? So the null hypothesis there would be that we don't need the quadratic term, beta 2 is equal to 0. Okay, so what we did yesterday was we did it in that way. We entered the terms as age followed by age squared. So that means that the order that the variables were considered in R is first we include age and then we include age squared. Okay, so that's what we did yesterday, and we got an analysis of variance table which looked like this. That gave really quite strong evidence, p-value 0.003, for the inclusion of age, and no evidence whatsoever for the inclusion of age squared, because we have a very large p-value here, it's 0.874. Okay, so once we've got age in, there is no evidence that we need to include age squared as well. Okay, however, we could do it the other way around. we could put in age squared first and then put in age. So if we change the order of age squared and age in the R command, so you now see we've got the I of age squared first. Remember that I there, I of age squared rather than just age squared, protects what's inside the brackets from the effects of what R tries to do to terms in linear models. So it ensures that it really is age squared that's being put in there. So I of age squared is first, then age. So if you do this, you can again do an analysis of variance table. And now, because we've put age squared into the model first, R tries to add age squared to the model before age. And what happens? Well, we get very strong evidence, again p-value 0.003, for the inclusion of age squared in the model. Then R thinks, well, given that we've got age squared, should we add age to the model? And finds no evidence. Again, this is a pretty large p-value, not quite as large as on the previous slide, but it's still nowhere near giving us any evidence against null hypothesis. So there's no evidence that we should include age. So if we add age first, there's evidence that we should do that, but then no evidence that we should add in age squared. If we add age squared first, there's evidence that we should do that, but then no evidence that we should add age. Okay? So if we look at the two tables, the entries, the rows that we get for age are different. So the sums of squares in the two tables in the age row are different numbers. Okay? And that's because in the first table, we've just haven't got anything in the model before age, we've just got a constant term. But in the second term, age squared is already included. Okay? Now, this happens, of course, because age and age squared are very much correlated variables. Okay? There's clearly a strong correlation between the age of something and the square of the age. So what's happening here is that the analysis of variance technique can't really tell us whether it's better to include age and then say, well, there's no evidence for adding in age squared, or is it better to include age squared and say, then there's no evidence for adding in age. So the analysis of variance method doesn't really help us answer that question. Okay? And that's it's not always going to be true. It's usually going to be true if you have two highly correlated variables. If you have two highly correlated variables, there will be very often evidence that you should include one of them. There won't be evidence that you should include both of them, because essentially the information that you need is already in from the first one that you've got. But it doesn't tell you whether it's actually better to include one variable or the other one. You know it tells you want one of them. You probably don't need both of them, but it doesn't tell you which of the two variables it's better to use. So in the tractor data, is it better to use age or is it better to use age squared? Okay, the analysis of variance method doesn't really tell you that. Later on, we will see some methods which do help answer that question later in section 2. Okay, so there is one more example in the notes which looks at a quartic model. So when we try and fit a degree 4 polynomial to a data set. I'm not going to go through the details of that example. You can read it and you'll see that the ideas are pretty similar to what I've just been saying. The question is the order in which you enter the variables matters, and it's not apparent from the analysis of variance which order is actually giving you the best answer. Okay, so at that point I'm going to finish chapter 1 of the notes and move on to chapter 2. So chapter 2 covers a number of topics in linear models. And in particular, we're going to think at first about how can we check the assumptions that we've assumed for a linear model to be a valid answer. And if those assumptions appear not to be satisfied, then what should we do? Okay, that's the first part of chapter 2 is going to be answering those two questions. So, I'm now on page 28, beginning of chapter 2. So, we want to check whether the assumptions that we made in our model are sensible, whether they're valid assumptions. Now, the assumptions that we made in our linear model concerned the error terms, the random part of the model, the epsilons. Okay, so I'll remind you in a minute what those assumptions were. Now, remember that you have the linear predictor, which for a given observation, I, is the xi transpose times the vector of coefficients beta, and the residual is then the observed value minus the linear predictor for that observation. Now, we then have an estimate of the betas, and from that we get a linear predictor for the estimated betas, and that gives us a fitted value, xi transpose times beta hat. And the difference between the observed value yi and that fitted value is the residual. Okay, so we can think of the residual as being an estimate of the random part of the model. So EI, the residual, is an estimate of epsilon I, the random part of the model for observation I. Okay, so that means that if we're interested in testing assumptions for the random part of the model, the epsilons, we can look at the data for the e's, the residuals, which is what we've actually got. We don't have the actual epsilons. We don't know what beta really is. It's what we're trying to estimate. So we don't know the epsilons. Our e's are estimates of them. So we can use the residuals to start thinking about how we can check whether the assumptions might be valid. Okay, so remember the assumptions that we had for the epsilon i's. So first of all, we assumed that they had zero mean. Now, I'm not going to concentrate very much on the question of whether that assumption is correct, because if it's wrong, then what that really means is that our linear predictor is wrong. That's not a sensible linear predictor. Okay, so we can always assume that if we've got a linear model, we can think about estimating the mean as the linear predictor, and then the random part is going to be 0. Okay, so I'm not going to think too much about the first one. Second one is that we assume the epsilon i's are independent of each other. So the random parts of the model for different observations are independent. We assumed that they all have the same variance, and remembered that we use this strange word, homoskedasticity, to describe them having the same variance. And we assume them to be normally distributed. So I'm largely going to be concentrating on checking these last three conditions: independence, homoskedasticity, and normal distribution. Okay, so as I said, we don't have the actual values of the epsilon I, because we don't have the true value beta I, we just have estimates of the betas, and hence we have the residuals, which are estimates of the epsilons. Okay, so we can't work with the actual epsilons, we have to work with the residuals, the e's, instead. Okay, so what we're going to be thinking about is checks using the residuals to see whether our assumptions appear to be satisfied. Okay, so the first thing I'm going to talk about is that there are some differences in the properties between the residuals and the random terms epsilon I that they're estimates of. Okay, so the residual, so the epsilons, the random terms in the model, we assume that those are independent and they all have the same variance and they have normal distributions with mean 0. Now, two of those things are true for the residuals. Okay? If the linear model is actually a correct model, then they are normally distributed and do have mean 0. However, the other two are not quite true. They're not independent and they don't have a common variance. We actually talked about this a little bit in the previous section. We defined a matrix M. Let me just look back through the notes and remind you where that was. So that was on page 12 of the notes in section 1.5. We had a matrix M. And that matrix we saw was related to the covariance matrix of the residuals. And a little bit after that, I mentioned what we actually got as that matrix M for the tractor data. And we see that the diagonal elements, which essentially are going to give you the variances, once you multiply them by sigma squared, you get the variances, are not all the same. They're a little bit less than 1, and they're not all the same. And the off-diagonal elements, which give you the covariances, are not 0. So there is a little bit of correlation between the residuals. Most of those numbers are quite close to 0 and negative. So there are actually small negative correlations between different residuals. Okay, so that's a reminder that you do have this difference in distribution between the residuals and the things they're actually trying to estimate, which are the epsilons, the random terms in the model. Okay, so one thing that we can do is we can correct for the fact that the residuals don't all have the same variance by normalizing them, dividing by our estimates of their standard deviations. And if we do this, we get what's called the standardized residuals. Okay, now sometimes there are advantages in doing this because it gives all the residuals the same variance. However, it also messes up their normal distribution. If you divide by an estimate of the variance, then estimate of the standard deviation, then you've destroyed the normal distribution. Remember that usually if you divide by an estimate of a variance, again, standard deviation, take the square root, then you tend to get a t distribution. In this case, you don't even quite get a t distribution. You get something with an approximate t distribution. So you've messed up the normal distribution and you've got something which has a t distribution instead. Now, in a typical linear model, the variation in the variances of the residuals is often not really enough to make it worth doing this and destroying the normal distribution and getting a t distribution instead. So a lot of the standard plots, and we'll see some of the standard plots that we use for model diagnostics in a minute, we just use the ordinary residuals and we don't move to these standardized residuals. Okay, so what we do with our residuals, a very common thing that we do with them is to plot them. So there are some standard plots which will give, if something is wrong with the model, they will often indicate that something is wrong with the model. There is a warning which I should give, that if your data set is small, these plots may not be very sensitive. Sometimes they may look bad even though in fact the model is fine. Sometimes, again, if the data set is small, they may not show up a significant problem with the model, but it may be very hard to detect a problem with the model in a small data set anyway. So that's perhaps not so alarming. You do have to remember that small data sets, it can be hard to actually tell whether there's a problem with the model or not. Okay, so there are several plotting commands that we use in R. I'll show you some code using these plotting commands on the next slide. Okay, so here are some plotting commands for the tractor data set. Okay, so the very first line here is something we've done before. We've fitted a linear model. So this is just going to be a straightforward linear model, so there's no quadratic term, just maintenance against age, to our tractor data set. Now, in this code, we've just called the fitted linear model A here, and that's simply a space saver. If you prefer, you could call it tractor.linear.lm as we did before, but it would take up more room on the slides. The next line, the one that says par mf row equals c2, 2, that is an R display control thing. It says that we set a 2 by 2 grid in the plotting display area, which allows us to have 4 plots visible at once. So the next 4 lines are each going to produce a plot. That line allows you to set them so that you can see them all at once in a 2 by 2 grid. And one thing I suggest is that after you've run this, you should then undo it by putting in the same thing again, but with 1 and 1 instead of 2 and 2. Otherwise, R will continue to use a 2 by 2 grid. Okay, so the first one is called an index plot, and it plots the residuals against the I. Okay, so I is just the order, the index of that observation. So for observation 1, it will give you the residual for observation 1. For the second, it will give you the residual for observation 2, and so on. We'll see that in a minute. The QQ norm gives what's called a QQ plot. I'll discuss that, I think, on the next slide. The third one, hist, that gives a histogram of the residuals. And the fourth one gives a plot of the residuals against the fitted values. Okay, so $fit gives the fitted values, and A.resid gives the residuals in the model A. So that gives a plot of the residuals against the fitted values. And again, I'm going to show you examples of this on the next slide. Okay, so this is what we get if we do that. We get 4 plots in a 2 by 2 grid because of that par line. And so we get index plot, QQ plot, histogram, and residuals against fitted values. Okay, so on the next few slides, I'm going to talk about these plots and how we can use them to get information. So what I'll have to do is I'll show you the discussion of the plot, and then I'll have to scroll back to this slide so you can actually see what the plot looks like again. Okay, so the second plot is what we call a QQ plot. So a QQ plot, if you haven't encountered it before, is a diagnostic for whether your data, which here is our residuals, A.resid, have an approximately normal distribution. So what they do is they take the observed data, they plot the quantiles of the observed data against the quantiles from a normal distribution. Okay, so if we look back at the plot, you'll see that it has theoretical quantiles on the bottom, -2, -1, 0, 1 and 2. And on the y-axis it has, you can only actually see the numbers -200 and 200. That gives a sort of idea of the range of the residuals. So we're plotting the quantiles of the observed residuals against the quantiles of a standard normal distribution. Okay, so if we actually have an approximately normal distribution for the residuals, then we should see something which is close to a straight line. And in that plot, allowing for the fact we only have 17 data points, which is not very much, that's a pretty good straight line. It could be a lot worse than that. Okay, so if you genuinely have a normal distribution, then you will get something which looks close to a straight line. If your QQ plot looks something like that, which suggests that the residuals are getting too high at the top end for the normal distribution, but at the bottom end are not actually going far enough for a normal distribution, then that suggests that you have a skew distribution of the residuals. And the same would be true if you had it going the other way around, so like that. So a curved QQ plot tends to suggest a skew distribution. Okay, so that would be again suggestive of a non-normal outcome. And if you get something like this, then this suggests, the points up here suggest that you've got your high residuals are too high for a normal distribution, and also because you've got this curve down at the bottom end, your low residuals, so large negative residuals, are too low for a normal distribution. This suggests that you're getting outliers at both ends. You're getting some which are too high for a normal distribution and also some which are too low for a normal distribution. So you're getting large outliers in both directions. So that suggests that you have what we call a heavy-tailed distribution. So something like a t-distribution would tend to give this sort of plot. So it suggests that we are more likely to get outliers than you would with a normal distribution. So any shape like this in the either of these in a QQ plot is a bit alarming for the assumptions. Now, as I said, in our tractor data set, it looks pretty good actually. It looks like a pretty convincing straight line. Okay. A third plot that we had was a histogram. So we plot a histogram of the residuals, and we would hope to see something which looks like the shape of a normal distribution. So let me go back to the plots, which were here. Now, I'd have to admit that this isn't the most convincing normal distribution that I've seen in the histogram. So that might look somewhat worrying. However, really, with only 17 data points, the histogram isn't very sensitive. So you will quite often get something which doesn't look very convincing if you take a sample from a normal distribution with only 17 points. So although the histogram doesn't look brilliant, it doesn't look that bad either to be worried about it for such a small data set. Okay, so the first plot that I did, so this was the one where we plotted the residuals against the index number of the observation. So the test here is whether there's a problem with independence. So if there was a problem with independence, you might find that observations with adjacent observation numbers, which would suggest they were next to each other in the data set, they might be correlated. You might have an effect that you would tend to get a high residual in one term, then you get another high residual in the next term. That might be a typical way in which you would see non-independence. Okay, so the index plot is trying to see whether adjacent observations in the data set might have a correlation. So if you did have that, then you would tend to get similar residuals for adjacent observations. So you would tend to get a pattern where you didn't get what looks like a random scatter in the plot. You would tend to get one value close to the next value. So things would be going up and down more slowly. Okay. Again, 17 data points isn't very much, so it's quite hard to see whether there's a problem with a data set of this size. Let me go back to the picture again. I don't see anything in that picture to be alarming in that sense. I don't think there's a particular tendency for points to be close to each other. I mean, you do sometimes see adjacent points close together, so residuals 2 and 3 are close together, for example, but there's no particular tendency for that to happen. It's sometimes happening, but not often enough to be alarming. Okay. So the final plot, which is the bottom right one in the table of plots, is the one where we plotted the residuals against their fitted values. And the main purpose of this one is to test whether we really have an assumption of homoskedasticity. Okay, so heteroskedasticity, which is when we don't have homoskedasticity, most often arises because you have a larger variation as you have a larger fitted value. Okay, so potentially larger values of the observed variable have larger variance. Now this, there are quite good reasons why this can happen. In many settings, your observed values are constrained to be positive. They are in this example because we're looking at maintenance costs. You can't have maintenance costs which are negative. So the response variable can be constrained to be positive. Now if the fitted value is small, so the mean is fairly close to 0, and the random variable can't be negative, its variance is going to be fairly small. If you have a small mean, close to 0, of a random variable which isn't negative, there's not much room for it to vary around its mean. So the variance is going to be quite small. Whereas larger values have more room to vary around their mean, so you might expect that the variances could be larger. So this is quite a common thing that can potentially arise. Okay, now what would a plot where heteroskedasticity of that sort was a problem look like? Well, it would probably look something like this. Okay, so the residuals for plots for observations with fitted values close to 0 are going to be quite close to 0. Okay, so things here are going to have a small variance. But over here, once the fitted values are larger and there's more room to vary about 0, we'd get more variability. So we'd get something which looks a bit like this. The residuals, the variability in the residuals fans out as we move, as the fitted values increase. Okay, so you get a plot which looks like this. So if you get a plot of residuals against fitted values that looks like this, that is immediately alarming and suggests that we have heteroskedasticity in the model, and that means there may be problems with having used a straightforward linear model to fit it. Okay, now there might be other patterns as well indicating different types of dependence of the variance on the fitted value, but this is the sort that you're most likely to see in practice, some sort of fanning out. Okay, if I just go back to the actual picture that we had, So it's now several slides back. So this one. Now, we don't really see that sort of pattern. There's no real evidence here of the variance being higher over here than it is over here. So although this is a context in which we wouldn't be surprised to see heteroskedasticity, there isn't really any evidence for it in this plot. So in this case, there doesn't seem to be any reason to be particularly concerned. Okay, we will see some examples as we go through this section which definitely do show reason to be concerned, and indeed will look quite a bit like that. Okay, one thing you might be interested in is, are there formal tests which we can use to see whether there is evidence that the assumptions are not satisfied? So there are. I'm only going to think now about the test for the normal distribution. Okay, so if the model fit is good, then as we saw a few slides back, the standardized residuals, so this is where we divide each residual by our estimate of its variance, those should follow approximately a t distribution, and it has the usual number of degrees of freedom for the t distribution in linear models, n the number of observations, minus p the number of parameters in the model. Okay, so what we want to do is to look at the standardized residuals and say, are they alarmingly large? If we compare them with a quantile of a t distribution with n minus p degrees of freedom, do they look alarmingly large? Okay, so we can say, well, if one of our standardized residuals is bigger than the 1 minus alpha over 2 quantile of our t distribution, then it looks like it's a bit too large. So we might be worried about that observation and call it an outlier. Now, there's something which you should be perhaps a bit worried about here, which is that we have n data points, and we're going to do this for all n of them. We have n data points, so we have n standardized residuals. So we're going to apply this test to n standardized residuals. Now, comparing an observation with the 1 minus alpha over 2 quantile of a t distribution is appropriate if you have one observation. But if you have n observations, you're enhancing the probability that one of them is a bit larger. So we need to be careful here about the concept of multiple testing. Okay? We've actually got lots of observations. Remember that if you do 20 hypothesis tests, and you use the conventional 5% significance level that people like so much, then the expected number of them that lead you to reject the null hypothesis is 1, because it's 20 times 0.05, even if the null hypothesis is true. So if the null hypothesis is true, you do lots of tests, the 5% level, eventually one of them is going to reject the null hypothesis. So we need to correct for that, which means that we use what looks like a lower significance level, so something lower than 5%, if we're doing lots of tests. Okay, so there are various ways of doing this. There's a familiar one which you may have seen before called the Bonferroni correction to deal with multiple testing. In these notes, we're going to use what's called the Schiedak correction. And the Schiedak correction is designed so that it controls the probability of getting at least one false positive. Okay? If you do lots of tests at the 5% significance level, then the chances are you're going to get a false positive eventually. So the more tests you do, you should lower your significance level to control the probability of getting a false positive. Okay? So let's say that we have n tests, and in each of those tests we're going to set the significance level, so the probability of type 1 error, so rejecting a null hypothesis which is true. We're going to set that to be beta. So the argument that I've just given says that as n gets larger, we're going to want beta to get smaller. Because if we keep beta to be constant, we're going to increase the probability of getting a false positive. And if n is large enough for fixed beta, the probability of getting a false positive will be very large indeed. So we're going to want our beta to get smaller as n gets larger. Okay? Now, if we do this, then the probability of getting a false positive, if the null hypothesis is true, okay, and the tests are independent, then the probability of not getting a false positive is 1 minus beta to the n. Because the probability of not getting a false positive on each test is 1 minus beta. So the probability of not getting a false positive at all, assuming independence, is 1 minus beta to the n. So the probability of getting a false positive is 1 minus beta to the n. So we've assumed here, obviously we've assumed that the null hypothesis is true, because we're looking at false positive probabilities, and we've assumed that the tests are independent. Okay, so if we want this to be equal to a fixed value alpha, say 0.05 for the conventional 5% significance level, then you can solve this equation. You want this to be equal to alpha, and you find that beta is 1 minus the nth root of 1 minus alpha. So that gives a formula for beta, and this formula is called the Shidach correction. Okay, so instead of using alpha as the thing we're going to use the quantile for, so we had 1 minus alpha over 2, we're going to replace that alpha with 1 minus alpha to the 1 over n, which comes from this Shidach correction argument, which will be smaller. Okay, and so then that means that overall our false positive rate should be the alpha which we wanted it to be. Okay, so this is similar to the Bonferroni correction. The Bonferroni correction uses alpha over n. If you expand that 1 minus alpha to the 1 over n using the binomial theorem, you'll see that the leading term that you get, the ones will cancel, and the leading term will be alpha over n. So in fact, the Shidach correction is asymptotically very similar to the Bonferroni correction. It's slightly stronger than the Bonferroni correction. Okay, so if we do that for the tractor data, so we've already seen our linear model for the tractor data, so maintenance fitted as a straight line plot against age, and we get the residuals. So we can get extract the residuals by, so A again is the name we've given to the R fit of the linear model. So A $resid gives the residuals for that fitted model. Okay, so obviously there are 17 of them. I'm not going to show all of them, but these are the first 3 that you will see in the R output if you do that. Okay, so those are the residuals. The standardized residuals, do using a function called stdres. That is not part of base R, so you need to load a library called MAS. So this library called MAS, MAS here stands for Modern Applied Statistics with S, so you may be aware there's a book of that title. This is the package which is associated with that book. So if you load the library, the MAS library, so you need that library command before you can use the standardized residuals command, we see that these are the standardized residuals. So now these should be approximately from a t-distribution, and the number of degrees of freedom, remember, is the number of observations, which was 17, minus the number of coefficients in the model, which was 2, so it'll be 15 degrees of freedom. So we need to compare these values with a t-distribution with 15 degrees of freedom. Okay, so I think this one, this standardized residual 3, 2.02, I think that's actually the largest of the standardized residuals that we get. So that's the one that we might be most alarmed by. But really, 2.02 is not very large compared with a t-distribution with only 15 degrees of freedom. Okay, so even if we didn't apply the Schiedat correction and we were looking at the 5% significance level, we'd be looking at t-distribution 15 degrees of freedom, and we'd be looking at the 0.975 quantile. Now that's actually a little bit more than 2.02, so even without the correction, that would not fail the test. That still looks in line with being from a T15 distribution. If we do apply the Schiedat correction, then our significance level, instead of the 0.975 there, we want to take our 0.05 and apply the Schiedat formula. 17 data points, so you take 1 minus 0.05 to the 1 over 17, and that gives us 0.003. So we actually want to look at the t-distribution with 15 degrees of freedom and this quantile, 1 minus 0.003 over 2. Now that quantile